In the previous video, we provided a numerical example that shows the two-effect estimator cannot, in general, be guaranteed to be centered around the average of beta s across states. In fact, it cannot even be guaranteed to center around a value inside the range of the true coefficients beta s from the smallest beta s to the largest beta s. This is a rather negative statement, but we find that this issue is not specific to the two-effect estimator. In the paper, we provide a more formal statement, but the idea is that identification for the average coefficient is going to be challenging when there is no restriction on the heterogeneity in beta s and when all states is somewhat affected by Medicare. So x at 0 is going to be strictly inside 0 and 1. In this situation, no estimator is going to be guaranteed to be centered around any point in the true range. I'm going to go over the proof for this claim because it's quite informative on where the identification challenge arises. Here, we're just going to focus attention on a special case with two states. And let's assume that state 1 has a larger XS0, but a smaller per unit insurance effect on the expenditure beta 1. We can normalize the time effect in the base period to be 0. Then the heterogeneous model can be written using the parameters of the state fixed effects alpha s, the time effect delta 1, and the state-specific coefficient beta s. Then the distribution of the data we see, which is just YSTs, is going to be characterized entirely by these parameters, together with the distribution of the idiosyncratic errors conditional on the exposure X. But what's special about this case is that we can actually write out a model with a different set of parameters, say theta prime, so that we would actually get the same distribution of the data. The difference between theta and theta prime is that we're going to perturb the time effect by a little bit, say delta, and then offset this perturbation by some increase in the state fixed effect and some decrease in the state-specific coefficient. So this little perturbation will not affect the data we observe in a statistical sense, that the data we observe is going to be distributed exactly the same under both theta and theta prime. And formally, this means theta and theta prime are observationally equivalent in the sense that we cannot distinguish between these two parameters based on the data we observe. This would also mean that if we're going to use an estimator, say beta hat prime, that depends on the data, its expected value must be the same under theta and theta prime because the data are distributed the same. However, we constructed the perturbation delta such a way that the range of the true coefficients beta 1 and beta 2 versus beta 1 prime and beta 2 prime will not overlap. And this means that the estimator for beta, the estimated beta hat prime cannot have an average value that's both lying within the range of true coefficients under beta and theta prime. This result coincides with what we discussed for the two-effect estimator previously, in the sense that it can estimate an average of the coefficients when lambda is 0, but once we change the lambda a little bit to allow for some treatment effects heterogeneity, the two-effect estimator starts to behave poorly and its expected value can lie outside the range of the true coefficients.